Welcome dear learners. Through this video, we are going to revise the topic of maxima and minima. The maximum and minimum value of a function shows physically interesting features under the differential mathematics, especially in calculus. It has a many application in the real life problems such as to determine maximum or minimum volume, area, slant height, total area of a sphere and many more. To determine the maximum profit and the minimum cost in the business sector is the main application of the maxima and minima. This method can solve many physical and practical problems in engineering sector. We will revise the definition of increasing and decreasing function, local maxima and local minima, then global maxima and global minima, and finally we will work out with some examples of finding extreme value of a function. Increasing and decreasing function. A function is increasing when its graph rises as it goes from left to right, and it is decreasing when its graph falls as it goes from left to right. Increasing or decreasing concept can be associated with the tangent line. In this graph, you can see the pattern of increasing and decreasing of a graph. Whenever graph increases, slope of the tangent is positive, and when the graph decreases, slope is negative. Let f be a function that is continuous on the closed interval ab and differentiable on the open interval ab. If f dash x is greater than 0 for all x in open interval ab, then f is increasing on closed interval ab. And if f dash x is less than 0 for all x in open interval ab, then f is decreasing on closed interval ab. But if f dash x is equal to 0, then f is constant on closed interval ab. Local maxima and local minima of the function. The local maxima are the largest values that a function takes in a point within a given neighborhood, whereas the local minima are the smallest values that a function takes in a point within a given neighborhood. Mathematically, a function f has a local maxima at c if f of c is greater than or equal to f of x, where x is near c, and f has a local minima at c if f of c is less than or equal to f of x when x is near c. Here we can see that for the graph of function f of x, we have two local maxima and one local minima in the given neighborhood. Global maxima and global minima of a function. A function f defined over a closed interval ab is said to have global maxima at x equal to c, where c belongs to closed interval ab, if f of x is less than or equal to f of c for all x belongs to ab, and it has a local minima in the interval ab if at x equal to d, f of x is greater than or equal to f of d for all x belongs to ab. In this graph, at point C, we have the largest value of the all maximum value, and at point D, we have the smallest value of all minimum value of the curve. So, point C and point D are global maxima and global minima of the function in the interval AB. Critical point of f. A point C in the domain of function f at which either f dash c is equal to 0 or f is not differentiable is called critical point of f. When the function has maximum or minimum values, then these are called extreme values of the function. To find the extremum value of the function, the following test is useful, which is named as second derivative test. In this case, in the step number 1, we have to differentiate the given function with respect to x to get the function f dash x and equate it with 0. Solve the equation f dash x equal to 0 for x. Let its root be c1, c2, c3. Then the function may be maximum or minimum at the values of x, which are called stationary points. Now in step 2, find f double dash x and substitute c1, c2, c3 in it and determine the sign of f double dash x for each value of x. Case 1. If f double dash c1 is negative, then f of x is maximum at x equal to c1. But if f double dash c1 is positive, then f of x is minimum at x is equal to c1. Now we will solve some example using this test. Find the greatest and the least value of the function x cube minus 12x square plus 45x. So in the first step, we have to differentiate f of x, which is equal to x cube minus 12x square plus 45x. So if we differentiate this, we get f dash x is equal to 3x square minus 24x plus 45. Then find out f double dash x here only, which is 6x minus 24. For maximum or minimum of f of x, equate f dash x with 0. We get 3x square minus 24x plus 45 is equal to 0. And if we solve this quadratic equation, we get the roots as x equal to 3 and x equal to 5. Thus, x equal to 3 and x equal to 5 are called as stationary point. Now, we'll check the value of f double dash x, which is equal to 6x minus 24 at this stationary point. So, at x equal to 3, f double dash 3 is equal to minus 6, which is less than 0. So, f of x has a maxima at x equal to 3 and the maximum value at x equal to 3 is 54. At x equal to 5, f double dash 5 is equal to plus 6, which is greater than 0. Therefore, we can say that f of x has a minima at x equal to 5 and the minimum value at that point is 50. So, this is the greatest and the least value of the given function at the stationary point. Next example is, divide the number 84 into two parts such that the product of one part and square of the other is maximum. Let one part of 84 be x. Then the other part will be definitely 84 minus x. Consider f of x is equal to x square into 84 minus x. This is the function which we have to maximize, because we have to maximize that the product of one part and the square of the other part. So we are letting that the one part is 84 minus x and other part square means x square. So here f of x is equal to 84x square minus x cube, and we have to maximize this. Find out f dash x, which is 168x minus 3x square. F double dash x is 168 minus 6x. For maximum or minimum value of f of x, we need to equate f dash x with 0, which gives us the two values for x. One is 0 and other is 56. These values are called as stationary point. Now f double dash x is equal to 168 minus 6x. Now substitute x equal to 0, f in f double dash x, we get f double dash 0 is equal to 168, which is greater than 0. That means f of x has a minimum value at x is equal to 0. As we are interested in maximum value, we'll substitute the other stationary point in f double dash x. So for x equal to 56, f double dash of 56 is equal to minus 168, which is less than 0. As it is less than 0, f of x has a maximum value at x is equal to 56. Therefore, the first part of 84 is 56 while the other part is 28. Because for x equal to 56, function has a maximum value. Therefore, the two parts of 84 are 56 and 28. Let's take another example. Divide the number 84 into two parts such that the product of one part and square of the other is maximum. Let one part of 84 be x, then the other part will be 84 minus x. Here we have to maximize the function which is the product of one part and square of the other. Consider that function as f of x, which is equal to first part into product of first part into square of the second part. For simplicity, here I have considered the second part as a x. If we solve this, we get f of x is equal to 84x square minus x cube. Find out f dash x, which is equal to 168 minus 3x square. So that f double dash x is equal to 168 minus 6x. For maximum or minimum of f of x, we have to equate f dash x with 0. That is equal to 168x minus 3x square equal to 0. This gives us the two values for x equal to 0 and x equal to 56, which are called as stationary point. Now f double dash x is equal to 168 minus x. We will put these two stationary point in f double dash x. At x equal to 0, f double dash 0 is equal to 168, which is greater than 0. So we can say that f of x has a minimum value at x equal to 0. But we are interested in the maximum value of the function f of x. So we will substitute x equal to 56 in f double dash x, which gives us the value minus 168, which is less than 0. So we can say that f of x has a maximum at x equal to 56. So from this we can conclude that 56 the one part of the 84 and 84 minus 56, that is 28, is the other part. Therefore the two parts of 84 are 56 and 28, which gives us the product of one part and square of the other part is maximum. The next example is an open box is to be made from a piece of square cardboard of side 18 cm by cutting off equal squares from the corners and turning up the sides. Find the maximum volume of the box. Here we have to find out the volume of the box first and then we have to maximize that function. So let x be the side of each square removed from the piece of cardboard. Therefore, the length of the side of the box will be 18 minus 2x centimeter and the height of the box will be x centimeter. Therefore, the volume of the box is equal to area of base into height. That is equal to 18 minus 2x square into x, which is equal to 4x cube minus 72x square plus 324x. If we expand this bracket, we get f of x equal to 4x cube minus 72x square plus 324x, which is the volume of the box and which we have to maximize. Find out the derivative of f of x, which is equal to 12x square minus 144x plus 324. Again find out the double derivative, which is 24x minus 144. Now for maximum or minimum of f of x, we have to equate f dash x with 0. So 12x square minus 144x plus 324 equal to 0 gives us the two values for x. One is 9 and other is 3. For x equal to 3, f double dash 3 is equal to minus 72. If we substitute x equal to 3 in the function f double dash x, which is 24x minus 144, the answer is minus 72, which is less than 0. That means volume is maximum at x equal to 3. And that maximum volume is equal to, substitute this 3 in the volume formula, which is 18 minus 2x whole square into x, which is equal to 432 cubic centimeter. This is what just the quick revision of the topic maxima and minima. Thank you very much.